Okay, I thought I would try my hand in trying to determine which Disney character you are most like. So as you can see, I have a good selection of cards. Now, it is true they're all hearts, but I do have a good selection of number cards and face cards to work with. Okay. Now, of course, we both have seen the cards here, so why don't we gather those up and we'll kind of give them a mix so that no one knows where anything is. In fact, if you were here, I'd have you randomly cut it. That would be just fine, okay? But since you're not here, I'll go ahead and just give it a Charlier shuffle. Okay, very good. So what we're going to do now is we're going to deal them out into a clock pattern here. Okay, so here we go. The top there may go off the camera view there. Now I created this diagram down here to kind of keep us on track for laying these out. Okay, since there's quite a few of them. Okay, so what I need you to do now is I need you to randomly choose a starting place. Okay, and it really is a free choice. You can start wherever you would like. And that fact will actually come out in the tutorial in just a few minutes. So let's say a person decides to start down here. Okay, so you chose a jack, okay? So what we're going to do is we're going to uncover these, and the very last one to be uncovered will be the person or the character you are most like, okay? So we're kind of leaving it to the powers of the universe to communicate to us that fact. Okay, so apparently you're not like Pinocchio, okay, because you've just turned him up. So how this is going to work is we're going to use this as a clock and go clockwise, and we're going to take the card value and count that many positions, and which will land us on another card which will flip up. And we'll do that until we get to the very last card, and that last card is going to be your avatar among Disney characters. Okay. Okay, so Jack, that's an 11, I believe, right, in as far as numerical value. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we turn this one up. Okay, there's Simba there, so you're not him. So 5. 1, 2, 3, 4, 5. Let's go down here. Okay, there's Alice. See a queen. Isn't that a 12, right? See, so 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. Oh, Peter Pan. Apparently you're not him either. 13. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay. Oh, okay, there's Mickey Mouse. You only have to count 1, so that's simple. So 1. Okay, there we go. Lady from Lady and the Tramp. 7. 1, 2, 3, 4, 5, 6, 7. Okay, I'll turn this one up. Oh, okay, Jiminy Cricket. Okay. So an 8 on that card. So let's see, 1, 2, 3, 4, 5, 6, 7, 8. Very good. So you're not Dumbo, apparently. And then 6. 1, 2, 3, 4, 5. Let's see, 1, 2, 3, 4, 5, 6. Wait, what's going on here? Because if we start counting from here again, we'll just go in a circle for all eternity. What is going on? Oh, wait. That's how the universe is going to communicate to us which Disney character is most similar to you. And which one is it then? Let's check it out. Oh, it's the Joker. It's the Mad Hatter. Oh, boy. I think I could have predicted that, because anyone watching a math card video has got to be a bit crazy. Okay. Oh, and also I just wanted to point out, in camera view, actually completely in camera view because I bumped the box, I have something underneath here. Let's just check to see what this is. Oh, I saw the future. I saw that you would indeed land on the Mad Hatter because you're just a little bit crazy. Okay. Okay, so how does this effect work? Now, of course, you don't need Disney cards for this. You can spin it however you want. It really is your choice. I just happened to have Disney cards and thought, okay, well, this would be a way to frame the whole thing. Okay, let me just bring out a write-up to kind of talk about this. Okay, so why does this work? Okay, so a little bit of this just for about 1 minute will be kind of technical sounding, and then from there I think most everyone will be okay. So to be able to give some background for what's going on here, we do have to dip our toes into abstract algebra. Now, some of you are very familiar with that branch of mathematics, whereas others aren't. But don't panic. Okay, so in abstract algebra, Z sub n refers to the set, collection, of integers, these are the whole numbers and their negatives, modulo n. Now what that means is modulo n, so like the integers modulo 3 would consist of the numbers 0, 1, and 2. Because the way that you use modular arithmetic is you divide the given integer by the value you've selected for n, so here it's 3. So every integer divided by 3, well, maybe focus on the positive ones for now for simplicity. Every positive integer divided by 3 will give you a remainder of 0, 1, or 2. Those are the only possibilities. So modular arithmetic is where we look at the remainder that results upon division by some other value. Okay, so that's all that means. Okay, so this set is denoted by Z sub n, so it's 0, right? Because you can always have a remainder of 0 when dividing by some other whole number, right? 1, 2, all the way up to n minus 1. And the operations involved here are addition and multiplication, but that's performed modulo n, okay? Now, Zn is used in various mathematical contexts, including number theory, cryptography, and algebraic structures. So definition, let n be an odd positive integer, and let this here be a permutation in Z sub n. We say that this sequence or this permutation has the long walk property, abbreviated LWP, if the following holds. So if a walk consists in always stepping from a position I to a position I plus B sub I, then there are only 2 walks. One that never leaves, so it's like a fixed point, and the other visits all of the other values. So in some sense, you'll stop on all of the other cards, which is actually what happened in our presentation, right? We turned over all of the cards except for the silly joker, right? So the joker was in a very special position relative to the card values in the rest of the packet, as we'll see. An example, a permutation of Z7, so this is the integers modulo 7, that has the long walk property is the following. 0, 2, 4, 6, 1, 3, 5. Okay, so I encourage you to check this out for yourself. Example 2, now this is the sequence that I used. It's a permutation of Z9 that has the long walk property, and here's the sequence. Now I slightly modified it, as I mentioned down here, and I think it's a good thing to do because you kind of hide the method a little bit. But the original long walk property sequence is 2, 4, 5, 6, 8, 1, 7, 3, 0. Okay, 0 is the one we're going to reveal. So this is the original sequence here. Now I have down here is I used the sequence in example 2, but I replaced the 2, 3, and 4 with equivalent card values modulo 9. Okay, so what does that mean? So instead of using a 2, I used a jack. Well, why is that going to accomplish the same thing? Well, it's because there are 9 positions in our circle, right? So going 2 in our walk is the same as going 11 for a walk, right? Because you're going to go all the way around in 9 steps, and then you're going to go 2 more. So we say that 2 and 11 are equal or equivalent modulo 9. Okay, and then you can see what I've done with the queen, right? So the queen, I put it in place of 3. Well, 9 plus 3 is 12. So going 3 steps will be the same thing as going 12 all together, because you'll go all the way around for the first 9 steps, and then you'll go 10, 11, 12. You'll go 3 more, okay? And then the king, similar thing. I've replaced the 4 with the king, so it will land at the same place. So it's just a way to hide the method a bit. I didn't really like this fact that it's 4, 5, 6. You know, I don't know if that would make people suspicious or something. So what I did was, you know, I replaced that one, and then this one over here with these face cards. Okay, so anyway, that's the secret. We're taking advantage of the long walk property for sequences in Z sub n. So thank you for watching, and maybe come up with your own routine that uses 7 values if you like. Again, thank you for watching, and take a look at other videos on the Absolute Math Magic channel.